Any of you that follow me on Instagram probably saw this picture go by last week. After the last laser video, a student from the University of Toronto contacted me and invited me to come see his laser lab, and since the timing worked out with some traveling I was doing, I was able to stop by for a visit. First off, I want to say a big thank you to Olivier. Thanks again for inviting me out, and it was amazing seeing the lab and very insightful. And thanks to the rest of the guys that showed me around. I got a lot of footage from this visit, so you'll be seeing clips from this trip in many upcoming laser videos. And seeing how the professionals do things gave me so many ideas for how I can improve my own work. The lab specialized in femtosecond lasers, and we're using them to generate high-speed electrons for imaging and diffraction applications. The laser pulses can reach energies of several terawatts, but last for only a few femtoseconds, as the name implies. To form these high-energy pulses, they use a wide array of different optical effects and mechanisms, many of which require the use of nonlinear crystals we've explored in previous videos. In the first entanglement video, we looked at a process called spontaneous parametric down conversion, where a high-energy input photon is split into two lower-energy photons that were hopefully quantum entangled. This lab uses a similar process called optical parametric amplification. Just like last time, a high-energy input beam is split into two lower-energy beams, but this time a second input known as the seed is also shot into the crystal at the same time. So now when the first high-energy beam, called the pump, splits, one of the photons will be the same wavelength as the seed in a sort of stimulated emission. So you end up with more photons of whatever color you set the seed to. Basically, this process lets you pass off energy from one beam to the other. Along with your signal output, you get a side product of a second output beam, whose wavelength is equal to whatever the difference between the pump and signal beams is, and it's known as the idler. You can actually see this in their setup. Here, the signal is a yellow and their idle looks red. I say that the idle looks red because there's so much power in these beams and because of their setup that some of the idle undergoes second harmonic generation to produce red light, which is what we're seeing. The idle itself is actually in the infrared and is otherwise invisible. The cool part is, because this effect generates two output beams, just like the effect we looked at last time, the light comes out in a cone. I managed to get a few pictures, and we even took a long exposure where we slowly moved the card we were projecting it onto, so that you could kind of see the cone in 3D. Either way, it looked very cool to see what this actually looked like. Olivier also showed me how sensitive this setup is to any adjustment. Adjusting the angle of the crystal even slightly changes the pattern and, importantly, the colors coming out. It also showed me that the cone grows much larger than I thought in a much shorter distance. All in all, this meant that my last setup wasn't even close to good enough to actually pull off generating entangled photons. So this week, I set off to start improving my setup significantly. The first thing I thought I'd try was building the biggest laser I could. More power makes all of this easier. So I scaled the TE laser up from 25 centimeters to 90 centimeters. I knew the chances of this actually working were pretty slim because of the physics that these lasers work on, but I wanted to test the upper limits and work my way down so I wasted less of the aluminum L channel at the cost of more time. The laser was built in exactly the same way as before, but the lamination sheets were interlaced to prevent arcing, and I switched to PVC tubes instead of zip ties for handholds. I also upgraded the power supply as my little boost transformer just couldn't charge things fast enough and would only fire once every couple of seconds. I soldered four 12 kilovolt microwave oven diodes into a full bridge rectifier, and added yellow wires for the input AC and color-coded wires for the positive and negative sides of the DC output. The input was connected to an old neon sign transformer, but you can't just connect to both terminals because of the way that these transformers work. Instead, connect to one terminal and the case of the transformer. But even with those upgrades, this laser just wouldn't laze. The problem is that these lasers are very sensitive to how fast they dump their energy through the gap. And the bigger the capacitors use, the slower they discharge. For a laser to be produced, enough nitrogen in the air needs to be energized to a high energy state, so that when it all comes crashing back down to their ground or low energy state, they release the light all at once. But that high energy state only lasts for about a nanosecond at atmospheric pressure. This giant laser's capacitors are massive compared to the smaller model, so their slower discharge time slows things down far too much. And on top of that, the overlapping laminate increases the capacitance even further, which further decreases the fire speed. I'm going to gradually rebuild and retest this laser at smaller and smaller sizes until I find the maximum size for these. Maybe in the future I'll build one that works under vacuum like the professional units, so that we can get much more energy out and a much higher fire rate. We can even experiment with changing gases to tune the output color. But for now I moved on to the next major improvement in my setup, proper optical table components. You've probably noticed my use of whatever random garbage is laying around for my stands and mounts for various components. If I'm going to be doing this seriously, I needed a massive upgrade. So I designed the first of which is a holder for the crystals like my KDP and my new BBO crystal. Speaking of which, thank you Nick for pointing me to the BBO sale after the last video. It just arrived, and if it works and is legit, you probably just saved me $900, and I'll be one step closer to making entangled photons. So thanks again. Since the goal was precision, I cut all the pieces I thought I'd need out of some black acrylic using the CNC mill. I've uploaded the SVGs I used to the Food Lab GitHub for anyone who's interested in making a set for yourself. I hope that by the time I'm done with these laser projects, I'll have a whole collection of DIY optical components. And if you've got improvements or other designs, feel free to send me an email and we can add those to the repository of parts so that anybody can use them. This first build is very simple, but a little bit labor intensive. The mill does a great job for the most part, but there were a few irregularities which I hope to correct in future iterations, so once they were cut out, I had a fair bit of filing to do by hand. Though I expected this regardless because most of the holes needed to be square, and you can't cut a square hole with a round mill. I just took my time and worked things until they were as tight a fit for structural pieces or ran smoothly for moving parts. The piece I took the most time to get right was the actual crystal mount. After getting things close, I would constantly do some filing, clean the piece, and then test fit the crystal, always wearing gloves to make sure that I didn't damage anything. The last step before assembly was to drill a hole for a set screw so that once the crystal angle was set, it can be locked in place, as well as some holes in the face of the crystal mount for handles so that it can be rotated. The assembly of everything was really quick and straightforward. First, the base is assembled. Using some UV adhesive, I glued a circle of cardboard to the outer ring. Then the inner plate and lower vertical support were press fit together. A nut and bolt were then used to hold the second vertical support in place, and a second smaller piece is glued in place to make sure that the upper assembly sits in the center of everything. The upper assembly is made of 4 pieces. 2 faceplates with smaller inner diameters, a middle piece with a larger inner diameter, and then the crystal mount which spins inside everything. After making sure everything spins properly, some copper wire was glued in place to act as handles for rotating everything. Then the crystal was glued in place. Finally, the whole assembly was glued together and then to the lower assembly. And that's all there is to it. I haven't finished putting together the BBO mount yet, but it's exactly the same, just with a smaller hole to accommodate the smaller crystal. Of course, when this was done, I wanted to give it a try, so I dug up every laser I could find, but after testing each one, none produced any interesting nonlinear effects. This isn't really surprising, as even though these lasers are all more than enough to burn things, they are still just too low power. As a last-ditch effort, I even disassembled my green laser to get the diode out of it. Since most green lasers, including mine, use second harmonic generation, and a nonlinear crystal to turn infrared light into green light, by definition they must have a strong enough infrared laser. But after extracting it, I found that the built-in optics focus the light directly onto a tiny crystal in the optical train, so until I have a different lens, I can't actually use this laser with my crystal. So while I work to make the next components, I also ordered a few lasers that have a bit more kick. You know, a couple of watts worth of kick. I've also ordered some special mirrors and other bits to make more complicated setups, and of course everything will have its own optical component to hold it in place. And that's all I've really got for this video. We'll pick the laser series up in a little while once the new ones arrive, and of course we'll be diving more into the cool stuff that I saw at the Laser Lab in future videos. Hopefully by the end of next month I'll have my new biolab built, and setting it up will be a video or two, and then we'll start putting it to use, so be sure to keep an eye out for that. And my new antenna arrived, so we'll be playing around with that in the near future as well. If you enjoy these videos and want to see more, then be sure to subscribe and ring that bell to get notifications when I post new videos. These videos are supported in large part by my amazing patrons, and we just passed our first goal. I'll be updating the goals and rewards shortly, and for those at tiers that receive them, the stickers just arrived, so I'll be shipping those out to you shortly. That's all for now, and I'll see you next week.